Hello, and welcome to my channel. Today I'm going to talk a little bit about storage trends. We'll look at it from the past and the present and the future. But did you know that the IT demand for storage is growing at 20 to 30% every year? And the demand for storage in 2018 was more than 30,000 exabytes. Forbes says that 79% of the 112 surveyed respondents in a 2017 survey believe that their current storage architecture will be insufficient to handle their storage needs over the next 5 years. So the storage is a very sought after commodity. And over the years, the different solutions that these storage vendors have brought have just created this huge alphabet soup of acronyms that I think we need to kind of pull apart and maybe define a little bit. So before we do that, let's delve in a little bit and talk about the past, because looking at the past, we get an idea of some of the things that were tried years ago that were kind of shelved, put on, and then abandoned, and then came back to life again later on. So let's first take a look at something called the SLED. This is the single large expensive disk, or the mainframe storage systems, otherwise the better known as directly attached storage devices, DASD or DAS. They were first introduced in 1954 by IBM with the RAMEC 305. The cost of the unit was $3,200 a month. You could only rent it, you couldn't purchase it at that time. And as you can see from the photo on the left, it took up quite a bit of room. It stored a whopping 3.3 megabytes of data, or about 5 mega words of BCD encoded storage. Over the years, the SLED improved. It offered a removable format from CDC, shown in the middle. And on the right side, it evolved into the all too familiar Winchester hard drives, which were enclosed and allowed for much faster transfer rates than was previously possible. However, SLED drives were very expensive. They cost anywhere from $90,000 to $275,000 when you could purchase them, but they were the fastest form of secondary storage for the time. They did require large amounts of space, cooling, and power, of course, and they went extinct in 1989 with IBM's introduction of the 3390. That was the last SLED produced, and it had a whopping storage capability of 22.7 gigabytes. But SLEDs didn't go away. SLEDs came to the microcomputer in 1980. They were introduced by Shugart, which is now called Seagate, in the ST506, which is shown here, that had 5 megabytes of storage on a 5¼ inch median. They were quite large, but they were inexpensive. I think the cost for the ST506 was around $1,600 in 1980. They weren't exactly fast in transfer rates, but they were low power and they didn't have very high cooling requirements. And over time, those evolved year over year. They expanded from the 5 megabyte to the 10, the 20, the 40, the 60, and so on, up to the drives we know today at 15 terabytes. I would also include SSDs and NVMe NAND flash as well, in that they are also direct attached storage. In 1987, David Patterson, Garth Gibson, and Randy Katz conducted a study and wrote a paper that showed how adding smaller disks could outperform mainframe SLED drives at a fraction of the cost. And so they named it Redundant Array of Inexpensive Disks, or RAID. And that this could be implemented in software or hardware devices. And it had one downfall, and that was because as you add devices to a storage system, they have a tendency to fail more often. And that's just the nature of the calculation. RAIDs were offered in a number of configurations. You have RAID 0, which was a striped disk. That was single disk drive failures was a total loss of data. And RAID 1, which is mere drives that are single drive failures, can be recovered from the working drive. That's typically, RAID 1s are typically found today in the enterprise as the operating system drives. If one of the drives fails, then the other one takes over the load and the operating system continues to function. RAID 2, which is a bit level striping with local parity. RAID 3, a byte level striping with local parity. And then there was RAID 4, which was block level striping with local parity. Those were all implemented for the military. And I don't know of any, I don't even think it's in use today by the military. In fact, I know it's not, and they have no commercial application at all. RAID 5 was block level striping with distributed parity. Those permit single drive failures, and but they're kind of slow to recover. They're shown on how that works on the picture on the lower left. RAID 6 offered block level striping with double distributed parity. That gave you a second chance in allowing 2 drives to fail before the RAID was lost. And mainly the reason for RAID 6 was that during a recovery of a RAID 5 system, it was very likely that you would have a second drive failure, mainly because the drives are probably all the same age. And so while you're stressing them trying to recover, another drive would probably fail during the same time frame. And so RAID 6 was a counter to that, and gave you a little bit better probability that you might survive the recovery process and be able to go on. But I do want to stress that RAID is not a means of backup. Don't rely on this for backup. It's meant for continuous operations and allowing the system to continue, but you have to realize that it is possible and very likely that you'll lose the RAID during a recovered operation. Hybrid RAIDs are also possible. Those are combinations of RAID 0 and 1 called 0 plus 1 or 1 plus 0, either one. And JBOD, which isn't technically a RAID, but it is part of the standard nonetheless. There's also a few other variants like RAID 50 and RAID 60 and a few others besides that. Since you had all this data now and you could access it fairly quickly, the next thing was the network access storage, or NAS, and that was to allow multiple clients to be able to access that data, which was first demonstrated in 1980, and that was the Newcastle connection by Brian Randall. He demonstrated remote file accesses across a set of Unix machines, and that NAS provides directory and file level sharing between multiple clients. And it does it by exposing a direct attached storage or a RAID array as a file system to the end user. That offers a fairly good speed and convenience, but it requires some more network bandwidth. And the network is the computer was the Sun's sales tagline that came about as a result of that. The protocols that exist in NAS are still present today, which are NFS and CEPH or SMB. Or SMB. And but the one downside that NAS has is that once the server is saturated, that is, you've exhausted all the ports on the machines to attach hard drives to, then you need a second NAS or move to another storage solution. And one of those answers came from the former enterprise companies that have been chased out of the enterprise data centers by the upstart x86 machines. They came back kind of with a vengeance, and they developed the storage area network. And Brocade introduced the term SAN in 1997 with the release of their fiber channel equipment as something brand new, which it isn't. Digital Equipment Corporation had their VAX clusters in the early 80s, which offered something very similar to that. You also had a number of other proprietary systems which offered clustered systems as well. But the joke was SAN was known as SLED's answer to NAS, or SAN is just NAS spelled backwards. But SAN connects servers to the storage usually through a fiber channel switch, and has basically 3 layers. You have the host layer, which is the the systems which have the interconnects to the fiber channel switch and to the Ethernet network, and expose the block storage, which is provided by the file systems on the storage arrays. They expose that as file systems and directories to the client, either through NFS, CEPH, iSCSI initiators, or in the case of a database client, would be exposed as a object store or a block store. The advantage to the SAN is that you can then take that data pool and slice it up into segments, and then use zoning to prevent unauthorized host access to the storage segments that you want to limit the users or the user types to be able to get to it. For example, you might set up a segment for accounting, you might set up one for payroll, you might set up one for engineering, and then restrict access to those segments based on the type of the person and the type of the machine being used to access it, and then control access to the machine to the user types and the groups of users. The one thing about SANs is that the servers which are used to access the storage are single points of failure. SANs are commercial, they are proprietary, and they're horrendously expensive. The SAN performance scales up, it is a scale-up architecture, but it is not what we would call a modern scale-out architecture. And we'll talk about that a little bit later. Once a controller has been saturated, you need to add a new SAN, and that's really the downfall with those, other than their high cost. So I'd like to talk a little bit and move toward the future. Those are things that were developed in the past. Now, I'm not saying that they're not still used. They most certainly are. We still have NAS, we still have SANs. They're still very prevalent, but those architectures have been supplanted with things that are much better than that. So one of the ones that came about was Sun was trying to address some shortcomings in the file servers, in the server file storage. So in 2005, they designed ZFS, and I know people call it ZFS, but Sun's an American company and it's ZFS. They were trying to particularly address the time to recover RAIDs, as well as being able to reduce the time that there would be a system downtime, and also allow for data compression and data encryption to increase the storage security. So they're also modern. They have copy on write, and they also do continuous data integrity and data repair. You can take snapshots, and you can do duplication as an option. The rebuild time is a lot faster with ZFS because they use data rebuilds. RAIDs use bit level rebuilds. But they do use a lot of memory, and if you have deduplication turned on, they use a horrendous amount of memory. But that's just the cost of speed and performance and security. The performance of ZFS will fall once you reach a Z pool of 70% full. And it used to be a big deal. It's not such a big deal anymore because you can simply add drives to the Z pool today. In some of the early versions of ZFS, you could not do that. So it was a little bit bigger deal, and having to migrate in order to add on an additional storage capability, but it's not such a big deal today. So we talked a little bit about scale up a few minutes ago. Let's compare it to what is scale out storage. Scale up, as we said, is that additional drive arrays are added to the controller until all the controller capability is exhausted. And that's the end of it. Once you reach that, you're done. Scale out, however, uses multiple servers with locally attached storage across Ethernet or InfiniBand, and to form your storage pools. And that is that data is distributed across the cluster, and there is a metadata component which is used to locate that data within the cluster. You can easily add new storage servers with little or no downtime. And data is replicated between the servers to provide redundancy. And again, it's not a source of backup. Don't depend on that for backup. But it does allow for continuous operations. Performance increases with the number of storage arrays until the network fabric is saturated. And at that time, then you would look to do things with the network in order to increase the performance, in order to continue to build out. But scale out will build into multiple petabytes of storage, multiples of petabytes of storage. So there was a number of early proprietary solutions. One was from IBM, and another one was from Oracle, and there was one from Google, of course. But the open source ones began in 2003 with Lustre FS, and that was developed by the Cluster File System Company as a shared cluster storage system for high-performance computing. And Sun acquired CFS in 2007. Oracle, of course, acquired Sun in 2010, and they came under the auspices of controlling the development of Lustre, and they didn't, to be honest, know what to do with it. So in December of that year, they spun it off to the open source community, but they did keep pieces of it for their proprietary systems. Lustre provides a POSIX compliant file system. It can store a maximum of 3.2 petabytes if you use the ext4 file system, but if you use the FS, you can go to 16 exabytes. The Lustre FS is open source with a commercial version, which was acquired from Oracle by Intel in 2018. Lustre is comprised of specialized servers. The metadata server is the MDS, contains the file metadata and namespace and locators in the data store to find it. Find the information that's scattered all over your object stores. And the object stores, of course, the OSSs contain one or more object data targets or drives or RAIDs or ZFS pools. And then the Lustre client provides access to the data stored within the unified namespace. I think the only other thing I'd like to say about Lustre is that it is active. I mean, the MacLeod people, which manage the open source development of Lustre, have been busy developing new releases of it. There was a period there where during the transition of the commercial part to Intel, where they weren't very active, and I think they were kind of uncertain as to what to do. But I don't know for sure what really happened there, but they are back and they're active. Lustre is typically deployed on Red Hat, and the clients can be deployed on Red Hat, Ubuntu, and SUSE. Gluster came about in 2005. It's not related to Lustre in any way and doesn't share any code from Lustre. Gluster also provides a POSIX file system. It's installed on top of a normal Linux file system, usually XFS. It also supports ext4 and ZFS as well. But it is designed for a shared cluster storage at scale for large files, and the Gluster community defines a large file as a file that's greater than 11 gigabits in size. It supports geo-replication so that as you make changes to one area as a Gluster pool, it can be replicated automatically for the purposes of disaster recovery to another site. It's recommended that you use 10 gigabit or higher for the Gluster server interconnect network, but it will work with 1 gigabit. It's just a heck of a lot slower performance. InfiniBand is recommended for larger server installations. The Gluster architecture is a lot more complex than I want to deal with in this video, so look for one on installing Gluster and how to set it up coming soon. And the rights to the Gluster FS software were acquired by Red Hat in 2011, but the open source community is still active and still developing new versions of the system. CEPH was introduced in 2007. CEPH is an object store at the core with other services providing block and file system support. Rados provides a block store capability to CEPH, which is compliant with Amazon's S3 and OpenStack. And then the Rados block service, or RBS, provides a full distributed block device to the CEPH client, such as QEMU, KVM drivers. And then the CEPH client provides a POSIX compliant file system to the end user. CEPH Rados can be configured to perform geo-replication, and that is something new in one of the recent releases. I don't remember if it's Manila or which other one it might be, but it is in one of the recent, it was released in one of the recent releases. CEPH architecture is a lot more complicated again than I'd like to get into here. Look for a separate video on that in the future as well. CEPH open source was the assets were acquired by Red Hat in 2014. CERN uses CEPHFS and are currently working on looking at it to replace their current proprietary-based storage system, which I think their proprietary one was 300 petabytes the last time I heard. The CEPHFS currently stores 6.4 petabytes on OpenStack, Cinder, and Glance, and this is as of 2019. And 1.09 petabytes on CEPHFS, HPC, and Manila. So they're currently actively working on the HPC side of things, but the CEPHFS reached production status in 2018. Red Hat acquired the assets to CEPHFS in 2014, and then they in turn were acquired by IBM in 2018. One of the new players, BGFS, was introduced in 2008. This offers a management service, has a registry and watchdog for the other services, such as the storage service, which provides the distributed user contents, and the metadata service, which stores access permissions and striping information, that is the location of the data elements that make up the file stored in the cluster. And then a client service, which mounts the file system to access the stored data. BGFS, just like Gluster, Lustre, and Ceph, runs on top of a Linux file system. It can be ext4, XFS, or ZFS. And BGFS has native Linux kernel drivers and does not rely on Fuse. That's one of its major differences. They, again, are a Red Hat only at this time, but I suspect they will get to the other releases of Linux soon. It's just those guys seem to be really busy in their development right now, just trying to get features into the system. So we've looked a little bit about at the past and the present. Those are easy. Now what we have to do is get out a crystal ball and guess as what we think might happen in the future. But you know, there is a few things that we know are going to happen. So let's look at the easy things that we know are going to happen in the short term. First, we know that PCIe 4 is coming to replace PCIe 3. And that's the first vendor to implement that will be AMD in July with their introduction of the X570 chipset and the AMD Ryzen processor, the version 3 processors. We also know that SSD NVMe controller devices have existed for some time for PCIe 4. There have been a number of Ethernet controllers that have been announced in 2018 for 200 gigabit Ethernet, and there were some demonstrations of 400 gigabit Ethernet also in 2018. The server attached storage, or SAS, has a standard for SAS 4, which is replacing SAS 3. That goes, of course, from 22.5 gigabits from the older 12 gigabit per second. Also, NVMe over Fabric has been around for some time, and that will replace NVMe NAND. And the reason for that mainly is because at scale, when you get up to 100 or more NVMe SSDs, you run into some pretty severe latency penalties with NVMe NAND, and that has mostly to do with the protocol of the NVMe stack in the enterprise. So NVMe NVMe over Fabric supports iWarp and RDMA, which would and Rocky, as well as Fiber Channel. I'm not going to get into the debate with Rocky and iWarp. That is a ongoing battle that's been going on for several years between Mellanox, which controls the Rocky standard, and Intel, which controls the iWarp standard. But I'm not going to get into that here. You guys, if you want to talk about that, be my guest, but I'm not going to get into it. NVMe over Fabric reduces the latency to about 10 microseconds while supporting thousands of NVMe SSDs. And the type of NVMe SSDs we're talking about are the solid state devices like the 3D XPoint and Intel Optane, not the NVMe flash drives. SATA 3, I don't know of anything that's coming to replace that. I think that is pretty much dead and will be replaced by NVMe. Spinning Rust drives, I think, will gradually disappear as the cost for SSDs decline. SSDs are already the largest devices available for the enterprise. You have even Seagate has their Nitro, which is up to 16 terabytes. Samsung has their 30 terabyte enterprise SSD at the time I'm making this video, and there is a California company that has announced a 100 terabyte SSD that will be available, if it's not already. And now the crystal ball. The current research that's been going on, Microsoft has been conducting research on DNA storage devices for about the past 5 years. And last year they demonstrated a working 1 gigabyte DNA storage device. And that has the propensity to store tremendous amounts of data for a relatively long period of time and occupying a very small amount of space. Now, currently, if I remember right, our current lifetime on storage is about 15 to 20 years maximum. And then we have to go in and refresh it. Whereas if we had something like this, that would be 50 to 200 years. That would be possible. The only problem with DNA storage right now is that the read and write times, of course, are very slow. The other thing to look at is skyrmions. Skyrmions are nanometer-sized structures in magnetic films. These spin on the surface of the magnet like a tiny vortex. They could store much denser quantities of data that's currently possible and offer data transfers at much less power. They've been successfully tested in liquid crystal. They could breathe life back into the hard drive, so I could possibly be wrong, and I hope I am. They are currently having, I would say, delays in trying to store and transfer data because they haven't figured out the best structure for storing that, making that data possible to store and retrieve. But I'm sure they'll get that worked out. The other research topic, which is way down the road from where we are today, is that IBM recently demonstrated storing 1 bit of data on an atom in 2017. Currently, a hard drive takes 100,000 atoms to store 1 bit of data. Now that would be a magnetic hard drive. The quantum computing storage is perhaps decades away, and really what IBM's trying to understand at this point is what happens at this level. I mean, how fast is it, how stable is it, and how long will the data persist for? So that's really the things that quantum computing storage is looking at. So it's probably decades away, between perhaps a decade away before we actually get to a working quantum storage solution, if at all. So I hope you enjoyed this look at storage solutions from the past and the present, and what I think might happen in the future. If you like what you saw, please leave a comment, like, and subscribe. And look forward to seeing some other videos on some of the other topics that we talked about earlier, like Gluster and CEPH. I don't know if I'll get around to BGFS or Lustre, but I might look into that if you guys want to see that as well. Let me know, and I'll see you again soon. Bye-bye for now.